Log on, tune in, find out. Another good idea from Cambridge.
Session this afternoon that includes wine reception, so welcome to that. Please switch off your mobile phones. That's the request from the session. And now we will have a talk by Professor Gan, who will speak on Dunkl operators for symplectic reflection algebras of wreath-product types.
Thank you very much for the invitation to speak at the conference. So I'll talk about a joint work with Pavel Ettingov, Victor Ginsburg, and Alexei Oblomkov. Okay. So I'll describe the construction of Dunkl type operators attached to finite subgroups of SL2C and their wave products. So there are a lot of explicit computations in this paper, and actually, so I'll try to do some of it in the talk. Okay, let V be a finite dimensional vector space over complex numbers, and let omega be from V tensor V to C, which is non-degenerate skew-symmetric bilinear form on V. Okay. So first, I'll record the definition of symplectic reflection algebras. So these algebras are attached to a group G in SP of V, which is finite. And we say that an element G in G is a symplectic reflection if G is conjugate to a diagonal matrix of the following form. So lambda, lambda inverse, 1 to 1, where lambda is not equals to 1. Okay, so now I'll denote by SR the set of symplectic reflections in G. And let's see, C will denote a function from the set of symplectic reflections to complex numbers, where S goes to C sub S, which is at G invariant. So C of GS, G inverse is CS for all G and S. And T will denote a parameter, a complex number. Okay. The symplectic reflection algebra H associated to the group G and the parameters T and C is defined by generators and relations in the following way. So first we take tensor algebra on V, semi-direct product with the group algebra of G, and we take quotient by the two-sided ideal generated by the following relations. So the relations are xy minus yx is equals to kappa xy for all x and y in V, where, so now I'll describe kappa. Kappa of xy is equal to t omega xy 1, where 1 is the element, the identity element in the group G, plus sum over all gamma, over all symplectic reflections S, C sub S omega of 1 minus S x, 1 minus S y S. So this is an element in CG. Okay, so first example of the first example is the case where V is just C2. So this example was considered by Crowley, Bovey, and Holland. Okay, so in the example they considered V is C2, G is gamma, which is any finite subgroup in SL2C. And so in this case, HTC is can be said explicitly. So you take tensor algebra on a two-dimensional vector space. So let's say you take a basis x and y. So it's tensor algebra generated by two elements x and y, semi-direct product with C of gamma, and quotient away by the two-sided ideal generated by the element xy minus yx equals to z, where z is of this form, t times 1 plus sum over all gamma not equals to 1, c gamma of gamma, which can be taken to be any element in the center of the group algebra of gamma. So my C gamma is not exactly the same as this CS, differ by some multiplicative constant. Okay. Okay. So now I'll introduce the wreath-product generalization of this. So the wreath-product example was written by Dunkl and Ginsberg. Okay, so I'll use L to denote C2, and gamma will always denote a finite subgroup in SL2C. Okay. So now we take V to be direct sum of n copies of L, and take G to be gamma n semi-direct product with the symmetric group Sn, and this sits inside Sp of V. Okay, so in this case, what are the conjugacy classes of the symplectic reflections? So we have the following. So first, for any element gamma in the group gamma, so I write gamma sub L to be the element 1 everywhere except in position L, you have gamma, and then 1 everywhere else. So this is regarded as an element in gamma n. Okay, and I'll write S. Okay, so when gamma is not equals to 1, these elements form one conjugacy classes for each conjugacy class of gamma. And we have another conjugacy class of symplectic reflections, namely elements of this form, SLM, gamma L, gamma M inverse. Okay. So SLM denote the transposition in Sn that swaps L and M. Okay. So how many parameters do we have? So in a case, so in this example, n equals 1 case. The number of parameters is the number of conjugacy classes in gamma. So here you have an extra parameter that corresponds to this conjugacy class involving transpositions. Okay. So we can also write down the H more explicitly in this case, since we know what are the symplectic reflections. So in this case, H of T K C. So here, K is the parameter that corresponds to this conjugacy class of symplectic reflections. C is the same as just now. Okay. So HTKC is tensor algebra on Ln, semi-direct product with CG. quotient by the two-sided ideal generated by the following relations. So first, how to commute two elements when they are in the same position. So commutator of UL and VL. So I write UL to mean the following. UL means the elements U in position L in Ln. Okay. So commutator of UL and VL is omega UV. So T times 1 plus K over 2 sum over all M not equals to L sum over all gamma S Lm gamma L gamma M inverse plus sum over gamma not equals to 1 C gamma of gamma. And when you commute things in different positions, commutator of UL with Vm is minus K over 2 sum over all gamma omega gamma U comma V S Lm gamma L gamma M inverse. Okay. So in the case n equals 1 is a special case. So in that special case, it is this algebra considered earlier by Crowley, Bouvier, and Holland. The other extreme case is, so you take any n and you take gamma to be trivial. Right? In that case, you get a rational Cherenkov algebra for GLN. So if gamma is trivial, so the wave product case is the same as the rational Cherenkov algebra. So let me now recall the Dunkl operators in this case. So the rational Cherenkov algebra comes from the symplectic reflections algebra when you take G to be W, complex reflection group, and V to be H, direct sum H dual. Okay, and so in this case, if Y is an element in H, then the Dunkl operator dy is given by the following. So it's T partial d dy plus half sum over all reflections alpha C alpha alpha Y over alpha S alpha minus 1. So regarded as an element in the algebra of differential operators on H rec semi-direct product with CW. Okay. So in this case, we have an embedding HTC into the semi-direct product DH rec semi-direct product with CW, where and so group elements G goes to G, X goes to X for all X in H dual, and Y goes to dy for all Y in H. So in the first talk this morning, the rational Cherenkov algebra is defined just as the subalgebra in here generated by G, X, and dy. But here I gave the definition by generators and relations. Okay. So now I'll describe how to construct analogs of Dunkl operators in the case of wave products. But first I'll describe it in the case where n equals 1, right, for this algebra. So in this case, we cannot just do something like this, right? So the problem is that the gamma action on C2 in general is not diagonalizable, right? Unless gamma is only in the case when gamma is the cyclic group, you can do that. So first, I need to introduce some notations for algebra of differential operators. So T will denote a torus C star n, and this T will denote the Lie algebra of T. And so I'll consider following situation where we have x to chi, a principal T bundle. And suppose x and chi are both affine varieties. So now the T action on x induces a Lie algebra map psi from T to vector fields dx to the vector fields which lies inside dx. So I'll say, right, it's like this. H goes to psi sub h. And now let rho be a homomorphism from T to NF. So this will be a finite dimensional representation of T. So for now, rho is just any finite dimensional representation. Later, I'll take rho to be something specific. And I'll write dxf for dx tensor nf. Okay, now, so now we have psi minus rho from T to dxf. So by psi minus rho, I denote the following this homomorphism. H goes to psi h tensor the identity on F minus 1 tensor rho h. Okay, so I'll consider this algebra of twisted differential operators on chi. I'll write it as in this way: d chi associated to rho. So this is d x f at t invariance. So by this I mean the centralizer of the image of t under psi minus rho. Quotient by dxf at t, image of psi minus rho. So this algebra X, so you can think of this algebra as the differential operators acting on functions of the following form. So if I take something like this, so U open in X and F from U to F. F valued functions on some open subsets in X, such that psi hf is equals to rho hf. Then d chi rho So elements in the chi-row act on such functions. Okay. Okay, so now I'll describe the construction of the Dunkl operators in a case n equals 1. And I'll make following assumption. So assume that the element zeta, which is minus the identity on L, is an element in my group gamma. So in gamma, we have this, I assume that I have this element of order 2. So this excludes the case of cyclic groups of odd order, but it covers all the other cases. Okay, and I'll write S be the subgroup in gamma consisting of 1 and zeta. Okay. So now I take my, so now I'll choose X and chi. So X is L rect in L, where, so now I'll say what is L rect. So L rect consists of vectors V in L's, such satisfying following condition. V is in L rect if and only if gamma V is not contained in CV for all gamma in gamma but not in S. And I take chi to be X, which is L rect mod C star. So this can be regarded as sitting inside P1 of L, which is CP1. Okay, and now I take F to be C2, and so now I'll explain what is my role. Okay. So in this case, our T is n equals 1, and T is just C. So I'll take rho to be this homomorphism eta to NF. So it's eta sense 1 to the following 2 by 2 matrix. So mu plus half, 0, 0, mu minus half, where mu is some complex numbers, which I will choose later. Okay. So I'll take eta to be of this form. Okay. So now we have d chi eta. So we think of d chi eta as an algebra of twisted differential operators on CP1. On CP1 acting on O mu plus half, direct sum O mu minus half. Okay. So now I'll write down formulas for the Dunkl operators. Okay, so for an element V in L, I write V star for the following linear function on L. So from L to C, where U goes to omega VU. And for an element gamma in the group gamma, I'll write omega gamma for the following quadratic function on L. So it takes U to omega U gamma U. Okay. And now for any element V in L, I write dV for the following operator. dV is 2 over gamma partial ddv plus sum over all gamma not equals to 1 or zeta. So recall zeta is this element of order 2 in gamma. So it's sum over all gamma not equals to 1 or zeta of the following. So C gamma, my parameter, and gamma V plus V star over omega gamma. So this is an element in D, L-rec, semi-direct product with C gamma. Okay, and I'll write dVF to be the following 2 by 2 matrix. So the entries are 0 minus V star dV0, regarded as an element in D, L-rec, F, semi-direct product with C gamma. So we are following theorem for n equals 1. And I set t to be a non-zero parameter, and if you renormalize, I set it to 1 over gamma. And I take the number mu to be the following. So minus c zeta gamma over 2 plus 1. So here the only important thing to observe is that, so mu is just some number that depends on c zeta, this parameter. Okay, and HTC has an embedding into the following. So D chi eta, semi-direct product with C gamma, but I have to take quotient by a two-sided ideal generated by zeta minus some sigma, where sigma is this 2 by 2 matrix, 1, 0, 0, minus 1, inside NF. So, so this map is just given by gamma goes to gamma and V goes to dVF. Well, for rational chaotic algebras, it is possible to come up with formulas for Dunkl operators if you know rational chaotic algebras, and then you work out the explicit formula. In our case, we just guess what the formula should be, and then we check the relations work. So here, of course, main thing you have to check is the so n equals 1. So basically, it's one relation, more or less. So I'll do this computation just to show how all these identifications work. Okay. So the main computation is this. So main computation for n equals 1. So I have to compute the commutator of dV, f, and dWf. Okay. So I take v and w in L. Okay, so I'm commuting these two matrices, 0 minus v star dv, 0, 0 minus w star dw, 0 minus 0 minus W star dW 0, 0 minus V star dV 0. Okay, so we get minus V star dW plus W star dV, and then here is 0 and 0, and here we get minus dV composed with W star plus dW composed with V star. Okay, so now I'll compute this. So I take W star dV minus V star dW. So this is, okay, so dV is given by that formula. So I have 2 over gamma W star partial ddV, okay, from here, and then from the second term, minus V star partial ddW, and plus, so now the second type of terms, I have sum over all gamma not equals to 1 or zeta, C gamma over omega gamma, and okay, so now from the first term, W star dV, I have a W star gamma V star and plus W star V star, but that will cancel with a term coming from here, V star W star, and minus V star gamma W star from the V star dW gamma. Okay, and now so you can check following. So 2 over gamma, so this is just this, and this term W star partial ddV minus V star partial ddW is minus omega VW of the Euler operator plus sum over gamma not equals to 1 or zeta C gamma, and now the numerator here, W star gamma V star minus V star gamma W star is a certain quadratic function, and it turns out if you compute what is this quadratic function, you see it's the same as omega V W times omega gamma, so the omega gamma cancel with the denominator. Okay. So I'm left with this term. Okay, so now you have the other entry in the matrix. So and similarly, so if you do a similar computation, so you get minus dV W star plus dW V star is equals to 2 over gamma omega omega VW 2 over gamma Euler operator plus 2 and plus sum over gamma not equals to 1 or zeta C gamma gamma. Okay, so now we have to make use of our identifications in our codomain here. Right. So first, the Euler operator is the vector field generated by 1. And now, so in the algebra d chi eta, right? So this is the same as eta psi 1 is the same as eta 1. And eta 1 is defined to be this, mu plus half 0, 0, mu minus half. Okay. So therefore, this commutator d of commutator of dvf with dwf is the following. So I have omega vw 2 over gamma. So in the above term, so I replace Euler by mu plus half. Right. So I have minus mu minus half, 0, 0. And here I replace by mu minus half. So I get mu plus 3 over 2. And then the other term, sum over gamma not equals to 1 or zeta, C gamma gamma. Okay. So now let me rewrite this in a nicer way. So this is omega VW, 1 over gamma, 2 over gamma. It can be written as the sum of these two matrices, half 0, 0, half, minus mu plus 1, 1, 0, 0, minus 1. Plus sum over gamma not equals to 1 or zeta, C gamma gamma. So now this is omega VW 1 over gamma, the identity matrix, plus. So now we substitute our definition for mu. So so mu is chosen such that minus of bracket of mu plus 1 is C zeta. Okay. And then we have the matrix 1, 0, 0 minus 1. So this is the matrix which I denote by sigma just now, plus sum over gamma not equals to 1 or zeta, C gamma gamma, which is the same as omega VW. So this is my T times 1 plus, so in so here in our codomain, I quotient by zeta equals to sigma. So this is C zeta zeta. So plus sum over our gamma not equals to 1, C gamma gamma. Okay. So now I will describe the formulas in the case n greater than 1. So of course, the first thing you do is you take the wreath product of your of the definition for n equals 1. But after you take the wreath product, you have an extra parameter k. So you need to do a 1 parameter deformation. Okay. So here, so I'll use following notation. So I'll write gamma VL star to be the following linear function on Ln. So it takes U1, Un to omega gamma V UL. And I'll use omega gamma ML to denote the following quadratic function on Ln. U1 Un goes to omega Um gamma UL. Okay, so first we can have this. So dVF L is 1 tensor product. Tensor, I put the operator dVF in position L. So this is inside D, Ln rec, F tensor n, semi-direct product with Cg, where G is gamma n semi-direct product with Sn. Okay, so we call F is C2. So here F is still C2. And I'll take a basis F plus to be 1, 0, F minus to be 0, 1. And I'll write F, this vector F, to be F1 tensor dot 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 tensor Fn, where each Fi is either F plus or F minus. So all these things form a basis for F tensor n. Okay, and I'll write F arrow negative m. So negative m means, so in here I have Fm, and I replace F. So Fm is either F plus or F negative. I always replace it by F negative. And I don't change the other positions. Okay. Now for any V in L, I'll define this RVML to be from the linear map from F tensor n to C L n rec tensor F tensor n semi-direct product with Cg. And RVML is given by following formula. So it stands F. So I define on the basis. So it stands a basis element F to one of the following three possibilities. So first I take half the sum over all gamma VL star over omega gamma ML tensor F negative M and S ML gamma L gamma M inverse. If Fm is F plus and Fl is also F plus. I send it to half sum over all gamma Vm star over omega gamma ML tensor F M negative S ML gamma L gamma M inverse. If Fm is F plus and Fl is F negative, and I send it to 0 if Fm is F negative. So this RVML can be regarded as an element in CLN rec tensor endomorphisms of F tensor n semi-direct product with Cg. And we define the operator Dunkl VL to be the following. So first I take D of VFL. So dVFL is defined just by placing dVF in position L. And plus sum over all m not equals to L of RVML times the parameter k. Okay. So this is an element in differential operator on Ln rec, F tensor n, semi-direct product with CG. So in this case, our T is Cn, and I'll take eta from T. Eta now goes from T to endomorphisms of F tensor n, and it's the one such that it sends these elements 1 to the identity tensor tensor mu plus half 0 0 mu minus half. And chi in chi now is Ln rec mod C star n. So this in P1 n copies of P1. And in this so in this case we think of d chi eta in this case as acting on the following: O mu plus half direct sum O mu minus half and exterior power n times. Okay. So similarly, we have this theorem for n greater than 1. So I also set T to be 1 over gamma. So our H, the symplectic reflection algebra for the wave product gamma n semi-direct product with Sn, so HTKC, and based into d chi eta semi-direct product with Cg over the two-sided ideal generated by zeta I minus sigma I. So zeta I means zeta in position I, so I from 1 to n. So sigma I means sigma in position I, and the identity matrix in other positions. So again, here the main thing to check is the relations goes to the correct relations, and again that is also by explicit computation, very nasty computations. So I forgot to say. So this map is just G goes to G, and V a vector V in L, and V in position L goes to Dunkl VL. Okay. So one has following corollary. So let E be the averaging idempotent in the group G. Then so now we multiply by E on both sides. Okay, so E H T K C of E. So this is called the spherical subalgebra, and it embeds in the following. So here you can also multiply E on both sides. So after multiply E on both sides, one can make some simplification, and you get D chi rho G invariance for some rho from T to NC, one dimensional. Okay, so now I'll say how you can get this EHE in another way. So this is by taking a radial part of some differential operators. Okay, so recall our gamma is finite subgroup in SL2C, and so to gamma we can associate a Dunkl diagram Q, diagram Q, and I'll take Q to be the associated affine Dunkl, and I'll put some orientation on Q. So Q is a quiver associated to gamma by Mackay correspondence, and a vertex I in Q corresponds to an irreducible representation, and I'll write as Ni. And for an arrow A from I to J, we can associate phi A, a linear map, from L to Hom Ni to Nj, such that this map is gamma equivariant. So of course, phi A is not unique because you can rescale. And I'll write QCM for Q. Disjoint union with a vertex S, and then I draw an arrow from S to the extending vertex in Q. Okay. So I have Q, and then I have the vertex that corresponds to the trivial representation of gamma. So I write that vertex as 0. Then I take another S. I take a new vertex S and draw an arrow from S to O. Okay. So I'll denote this by B. So of course, on other places I have some other arrows, Q. And I'll choose an orientation on Q in the following way. So I choose orientation on Q such that the extending vertex 0 is a sink, and all the other vertices are either source or sink. So either all arrows comes out or all arrows goes into it. So we can do this since we assume gamma contains zeta. So we exclude the case where you have cyclic with where gamma is cyclic group of odd order. Okay, and I'll let alpha be the following dimension vector for QCM. So it is n delta on Q. So this means n times dimension of Ni at vertex I, and I put dimension 1 at the vertex S. So now we can define a map J from Ln rec into the space of representations of QCM of dimension alpha in following way. So I have to say what is J of a point U1 to UN. J of U1 to UN is a representation of Q. So I have to tell you for how each arrow acts. So for the arrow B, it's just 1, 1 to 1. So this goes from C to Cn. And at arrow A, not equals to B, A is in Q. This is given by phi. So I use this the phi A. So phi A of U1 to phi A of UN. Now, we also have following. So our group G, which is gamma n semi-direct product with Sn, sits naturally in GL alpha. And our T, so C star n, also sits inside GL alpha in following way. So if I take T, which is T1 to Tn, then I'll send it to the following element in GL alpha. So at each vertex I have to specify what is GI of T. So GI of T will be in GL alpha I. So where GIT is, so I take T1 inverse to Tn inverse, tensor identity map on Ni. If I is a source, and we take it to be 1 if I is a sink. Then the embedding J that we wrote down earlier is G and T equivariant. Okay. And J induces the radial part map from, so this goes from differential operators on rep QCM alpha, which are GL alpha invariant, mod D rep QCM alpha, image of psi minus rho for some rho, to D chi rho G. So this is the map such that if I take a U open in rep QCM alpha, and f is a function such that psi hf is rho hf for all h, then the radial part of a differential operator D acting on f restricted to Ln rec is the same as first letting D act on f and then restrict. Okay. So then then one can check that the following. So the image of the radial part map is the same as EHE after you conjugate by a certain gamma analog of discriminant function. So if you take rational Charonic algebra, after you take radial part, you need to conjugate by something. So here we also need to conjugate by something, and after we conjugate, well, we get exactly EHE. Okay, and in fact, this algebra is isomorphic to EHE. Okay, so I'll stop here.
will just resume in half an hour, 3:30. Thank you.